Hello, young scientists. Today, let's dive into the fascinating world of motion, how things move around us. Do you remember how in your previous classes you learned about different motions? Yes, motion can happen in different ways, along a straight line, in a circle, or repeating again and again like a clock pendulum swinging. Looking at Table 9.1 on your screen, you can see familiar examples. Soldiers marching in line show linear motion, just like bullock carts moving straight on roads. Think about the hands of an athlete running a race. They move in circles. That's circular motion. And the Earth's journey around the sun repeats every year, making it periodic motion. Imagine watching a swing at the park. It goes back and forth regularly, just like a pendulum you studied before. That's periodic motion too. Understanding motion is like discovering the rhythms of nature itself. So, can you think of any other objects moving in these ways? Keep those examples in mind as we explore further. Now, take a moment. Pause for 20 seconds. And try to recall and categorize any motions you've seen recently into these three types. Welcome back! Let's get deeper into the types of motion. First, linear motion. Imagine you are watching soldiers marching in a straight line. Their legs and bodies move straight forward. That is linear motion. Movement along a straight path in the simplest form of motion. Similarly, a bullock cart moving straight on the road is another great example. Now, what about circular motion? Picture the hands of an athlete running a race. The arms swing around in circles. That's how circular motion works, moving along a round path. Another example is a bicycle pedal, moving in a circle as you cycle. Periodic motion is fascinating because it repeats. Think of Earth's movement around the sun. It cycles once every year. The swing in a park goes back and forth just like the pendulum in a clock. This regular repetition over time is periodic motion. To help remember, linear is straight, circular is round, and periodic repeats again and again. Now let's pause. Think about these three motions and try to imagine other activities or objects around you that show these motions. See if you can find them in your home or school. Pause for 20 seconds and reflect on new examples you can find. Welcome to this intriguing part of motion, understanding slow and fast movements. Every day we see cars, buses, bicycles, and people moving at different speeds. What makes one vehicle faster than another? It's all about how quickly they cover a certain distance. Speed is simply how much distance an object travels in a specific time. If you have ever raced your friend or watched a marathon, you notice that whoever covers the distance in less time is faster. For example, a bus usually moves faster than a bicycle on the same road. Imagine you start pedaling your bicycle just as the bus begins to move. After 5 minutes, you would have covered less distance than the bus, right? That's because your speed is less than the bus's speed. Speed is an important scientific quantity, and understanding it helps us in transportation, sports, and even animals' movement. Later in this lecture, we will learn the exact formula to calculate speed. Now reflect. Have you noticed objects or vehicles moving faster or slower in your neighborhood? Why do you think their speeds differ? Pause for 20 seconds and think about it. Let's explore motion practically with Activity 9.1. On your screen are two figures, Figure 9.1 and Figure 9.2. Figure 9.1 shows cars and vans positioned on a road moving in the same direction. Now, Figure 9.2 shows where these vehicles are after some time. By comparing where each vehicle started and where it is later, we can determine how far each has traveled. The vehicle that has moved the farthest in the same time is the fastest, and the one that has moved the least is the slowest. Notice the lanes, vehicle colors, and spacing carefully. For example, you might find that the red car moved a greater distance than the white van. Through this simple observation, we learn that motion speed depends on distance covered and time taken. This activity is the foundation of the scientific understanding of speed. Take a moment, pause for 25 seconds to study the pictures and answer. Which vehicle is moving fastest and which is slowest? Let's understand how multiple vehicles moving on a road interact scientifically. Looking at figure 9.1, you see cars and vans moving forward on a two-way road with lanes marked by white dashed lines. These lanes are crucial. They help vehicles move in an orderly fashion to avoid collisions. The spacing between vehicles is also important for safety and smooth traffic flow. Drivers keep safe distances based on speed, weather, and road conditions. Scientists and traffic engineers study these patterns to manage roads better. They use the formula shown in equation, Q equals N times V. Here, Q stands for traffic flow. How many vehicles pass a point in a certain period? The letter N is vehicle density, number of vehicles per unit road length. The letter V is the average speed of vehicles. This helps us measure how busy or free the road is. Such understanding supports designing safer and faster roads. Now pause and ponder. How do you think increasing vehicle speed changes traffic flow? Take 20 seconds to think about it. Let's look at figure 9.2, which displays the position of vehicles after some time on the road. The road has two lanes, divided by broken white lines, allowing vehicles to change lanes safely. Notice the cars in different colors: white, green, blue, yellow, red, and light blue, plus a larger van. The positions of the vehicles have changed compared to figure 9.2. Some have moved forward more than others. By comparing these positions and knowing the time elapsed, we can calculate the distance each vehicle traveled. Here's the essential formula. Distance equals speed times time. This means if we know how fast a vehicle goes and for how long, we can tell how far it traveled. This simple relation underpins much of kinematics, the branch of physics that studies motion. It's like measuring how far your bike rides on a vacation. Now pause for 20 seconds and think. If two vehicles have the same speed, but travel for different times, what happens to the distances they cover? We've covered quite a bit on motion today, haven't we? Let's take a quick recap to make sure the key points stay with you. Remember, motion happens in different ways: linear, circular, or periodic. Soldiers march in straight lines, bicycle pedals spin in circles, and swings oscillate back and forth periodically. Speed is how fast an object moves. It helps us describe motion better, whether slow or fast. We used images of vehicles on a road to visualize motion and speed. Science is everywhere. These concepts help us understand travel, sports, even how animals move. As you notice motion around you, keep these ideas in mind to appreciate the science in the world. Before we wrap up, take a moment to reflect. Why do you think understanding motion and speed is important in daily life? Pause for 20 seconds to consider. Now let's apply what we've learned with a practical example. Imagine a car traveling 150 kilometers in 3 hours. How do we find out how fast this car was going on average? We use the formula speed equals distance divided by time. Here, the total distance is 150 kilometers and the total time is 3 hours. Step 1. First, we identify the distance, 150 kilometers. Step 2. Next, the time, 3 hours. Step 3. Now apply the formula. Speed equals 150 kilometers divided by 3 hours. Step 4. Calculating gives us 50 kilometers per hour. Step 5. That means the car moved on average at a speed of 50 kilometers per hour. This step-by-step approach helps us understand motion numbers precisely. Isn't it fascinating how this simple formula explains how fast objects move? Pause for 20 seconds. Can you think of other examples where calculating speed is useful like this? Let's take a closer look at two vehicles from the images of figures 9.1 and 9.2, Vehicle A and Vehicle B. Both start moving at the same time, and after a certain time interval, their new positions are recorded. Step 1. Vehicle A has moved 300 meters, and Vehicle B has moved 150 meters. Step 2. Since the time is the same for both vehicles, Step 3, we calculate speed by dividing distance by time. The one that covers the greater distance in the same time must be faster. Step 4. Hence, Vehicle A is moving faster than Vehicle B. This simple comparison helps us see how scientists and engineers measure speeds in real life. Take 20 seconds to think. Can you suggest scenarios where knowing which vehicle is faster would be important, such as in emergencies or racing? You might wonder, why do drivers keep a distance from the vehicle ahead? It's because motion and speed directly affect safety. When vehicles move fast, they need more distance to stop safely if something unexpected happens. Understanding motion helps traffic experts set rules about safe distances and speeds. For example, fast vehicles must keep larger gaps because their stopping distances are longer due to higher speed. Lane discipline, visible in Figure 9.1, helps prevent collisions by organizing vehicles sharing the road. This science of motion is critical not only for travel, but also for saving lives on the road. Imagine if there were no rules. Accidents would increase, making roads dangerous. Think about road safety next time you travel. How does obeying speed limits and maintaining distance help everyone? Pause for 20 seconds and try to imagine driving at different speeds in busy traffic. What changes do you observe in safety? Let's uncover the basics of kinematic, the branch of physics that describes motion. It tells us how objects move by studying quantities like distance, time, and speed without worrying about what forces cause the motion. The fundamental relationship here is distance equals speed multiplied by time, which you've seen earlier. This is simple but powerful. This helps us understand everything from how fast a cricket ball moves to predicting arrival times of buses or trains. Knowing this allows athletes to pace themselves, drivers to plan trips, and scientists to analyze natural phenomena. As a quick exercise, imagine running a race. If you run at 5 meters per second for 10 seconds, you'd cover 50 meters. That's distance equals speed times time. Pause and consider. Can you estimate how far you would travel if you walk steadily for 15 minutes at a uniform speed? Think about your answer for 20 seconds. Let's move towards a more advanced understanding. Periodic motion. This is a type of motion that repeats itself after equal intervals of time. Think about a swing in your park moving back and forth, or the pendulum in a grandfather clock ticking steadily. Earth's journey around the sun is a grand example. It repeats every year, creating seasons. Periodic motion not only helps us understand nature's rhythms, but also powers technology like clocks and watches. These repetitive movements are predictable, which is why they are crucial for measuring time accurately. Without periodic motion, timekeeping would be impossible. Imagine powering a clock with a pendulum. Its steady back and forth is perfect for marking equal seconds. Now pause for 25 seconds and imagine how periodic motion could be useful outside clocks. What other technologies or natural phenomena might use repetitive movements? Let's perform a classic physics experiment, observing periodic motion using a pendulum. You need a string fixed at one end and a bob attached at the other end so it can swing freely. Step 1. Pull the bob gently to one side and release it. You will see it swinging back and forth. Step 2. This swinging motion repeats after every fixed interval of time. That's periodic motion. The pendulum is famous because its swing time helps us keep track of time in clocks. Have you ever wondered how a grandfather clock keeps ticking steadily? It's because of the pendulum's uniform periodic swings. Try to count the number of swings in 1 minute and observe if it remains steady or changes as time passes. Pause for 30 seconds. Can you notice how the pendulum's motion repeats? Think about why it might slow down and what would happen if the string length changed. As we end today's fascinating journey into motion, remember that motion is everywhere. From the way your bicycle moves to how nature cycles through seasons. Knowing different types of motion, linear, circular, periodic, and how fast things move helps us travel safely and efficiently, improves our sports performances, and is crucial in engineering better machines. Think about clocks that tick reliably because of pendulums, or traffic flow controlled scientifically to prevent chaos. Science opens the door to curiosity, so keep your eyes open in everyday life for examples of motion and speed. Ask why and how things move the way they do. That's the spirit of a scientist. Before we finish, here's a fun imagination challenge. Picture yourself as a tiny observer sitting on a bicycle pedal moving in a circular path. What motion type do you experience? How fast do you think you move per minute? Think about it and share your thoughts next time.